Hello there. We had seen in the earlier lecture how to define a vector space and seen ample examples regarding the same, and also how a subspace of a vector space is. Also, we have dealt with lot of exercises dealing with subspaces. Now we are moving on to one of the important concept of this vector spaces, which is nothing but basis and dimension. So in this section, we are going to define what is a basis and what is a dimension, and also some examples related to it. Suppose if we have a vector space V defined over a field F, a subset S of V is said to be linearly dependent if there exist distinct vectors alpha 1, alpha 2, etc., alpha n in S, and some scalars C1, C2, etc., Cn in F, not all which are 0, such that the equation C1 alpha 1 plus C2 alpha 2 plus etc. plus Cn alpha n is equal to 0 is satisfied. So we need to say that a subset S of V is said to be linearly dependent. For that, what should we need? We need distinct vectors coming inside this S and scalars coming from F which are not all 0, such that their linear combination is equal to 0. If that happens, then we say that the set is linearly dependent. And if we cannot find such distinct vectors from S and scalars which are not 0, such that this doesn't happen, then we can say that the set is linearly independent or not linearly dependent. If the set S contains only finite number of vectors, we can say that those vectors are linearly dependent rather than saying that the set is linearly dependent, or simultaneously those vectors are linearly independent, or instead of saying that the set is linearly independent. So the fact which is defined can be easily understood from this example. Suppose we are considering the vector space R2 over R, or we can, according to our notation here, it can be even called F2 over F. Both are the same when we are moving along the textbook. So what I'm going to do is I'm going to define a set S1 which is equal to set ordered pair 1 2 comma 1 0. Definitely this S1 is a subset of R2, right? And also I'm defining an S2 which is equal to set 1 2 comma 2 4. That is also a subset of R2, and I'm claiming that S1 is linearly independent and S2 is linearly dependent. Okay, we are going to illustrate how this definition goes. For S1, we are saying that there exists no C1 and C2 that belongs to this field R, which are both not zero, such that C1 into 1 2 plus C2 into the ordered pair 1 0 is equal to 0. So this 0 is nothing but the additive identity in V. Okay, so here that will be 0 0. Okay, suppose we are assuming on the contrary that suppose such all these statements are satisfied. Okay, suppose if, okay, our claim is that this does not exist. We are assuming that it is existing. Okay, if they exist, that means this equation is satisfied for all those quantities. That means C1 plus C2 is equal to 0, and also 2C1 is equal to 0, that means C1 will be 0. So we need them to be non-zero, right? So it is a contradiction. That means S1 is linearly independent. Okay, as for S2, we know that this can be written like this: minus 2 into 1 2 ordered pair 1 2 plus 1 into ordered pair 2 4 is equal to ordered pair 0 0, and we know that this minus 2 and 1 will belong to the field R. Both are non-zero, so we got a linear combination like this. That means it is linearly dependent. In the earlier case, in S1, we could not find such C1, C2, and the equation was not generally satisfied, so that we said that it is linearly independent. Here it is linearly dependent. That's how uh, the linearly dependent sets and independent sets are defined. And from that, we have some assumptions which is left for you to prove 1 to 4. So all of them are very easy statements. The first statement is that any set which contains a linearly dependent set is linearly dependent. Okay. So we know that suppose if S1 is subset of V, suppose if it is linearly dependent, that means there exists alpha 1, alpha 2, etc. Alpha n belongs to S1, and C1, C2, etc. Cn belongs to the field F, such that C1 alpha 1 plus C2 alpha 2 plus etc. plus Cn alpha n is equal to 0. Right. So whenever this S1 is contained in S2, we know that all these alpha 1 etc alpha n are in S2 too, S2 also, right? And also the linear combination that is equal to 0 is satisfied there. That means S2 is linearly dependent there, right? So such logical reasons can make us understand that any subset of linearly independent set is linearly independent. You have to prove this statement. Any subset of a linearly independent set is linearly independent. The third one is any set which contains the zero vector is linearly dependent for, because 1 into 0 is always 0. So whenever 0 is a vector coming there, we get a non-zero constant coming from the non-zero scalar coming from the field F. So third can be proved like that. And how can you prove two? The logic is, we if we have a subset which is happening to be the subset of a linearly independent set. If the subset is linearly dependent, that means the set we are discussing will also be linearly dependent. See, suppose if we have S subset of T, okay, that is a subset of the vector space V, then if S is, we have to say that any subset, if T is linearly independent, we are assuming that T is linearly independent, okay, linearly independent, then we have to say that S is also linearly independent. For that, how can we do? You can assume on the contrary that S is linearly dependent. Okay. S is linearly independent will automatically mean T is linearly independent. So that will make a contradiction there. That's how you can prove that easily. Okay. So what about the fourth? The fourth says that a set S of vectors is linearly independent if and only if each subset of S is linearly independent. That is, if and only if for any distinct vectors alpha 1 etc alpha n of S, C1 alpha 1 plus etc plus Cn alpha n is equal to 0. That will imply every Ci is 0 involved in the equation. The next definition is what is called basis. We have V to be a vector space. A basis for V is a linearly independent set of vectors in V which spans the space V. We had seen what is the word span, the term span to mean. It means that a set, the linear combination of those vectors can form the whole space, right? So if we can find a set of linearly independent vectors in V such that they are also spanning the whole of V, then we say that that set is a basis. The space V is called finite dimensional if it has a finite basis. These are all easy things to understand. We'll illustrate them with an examples. Them with examples. You can see example 2. Suppose F be a subfield of the complex numbers. Fine. In F3, we are considering the vectors alpha 1, alpha 2, alpha 3, alpha 4. You know that these are all three tuples. Okay. And we are claiming that these four of them, these four vectors, that is the set alpha 1, alpha 2, alpha 3, alpha 4 is linearly independent. The set is linearly independent, or these vectors are linearly dependent. You can say in any ways. Since why? Because 2 alpha 1, you can verify it. 2 alpha 1 plus 2 into alpha 2 minus alpha 3 plus 0 into alpha 4 is equal to 0. So that means we have a combination of them, right? That means this alpha 3 can be written as a combination of the other two. Okay. Uh, or anything vice versa. So that satisfies our definition for linear dependence of the vectors. See what was our definition of linearly independent and dependent vectors. A subset is said to be linearly dependent if there exist distinct vectors alpha 1 etc alpha n. So here we have four of them and scalars c1 c2 etc cn, not all of which are 0. Here not all of them are 0, only one is 0, right? The other three constants are, see here c1 is equal to 2, c2 is equal to 2, C3 is equal to minus 1, C4 is equal to 0. Only C4 is 0. Not everyone is 0, right? So that means it satisfies the definition of linear dependence of vectors. So these four vectors are linearly dependent. Okay, now consider the vectors, you're calling it epsilon 1, epsilon 2, epsilon 3, which are the three tuples 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay, these three vectors are linearly dependent. You can check them out and they are very important. Note them out. Okay, suppose if they are not linearly independent. Okay, that means C1 epsilon 1 plus C2 epsilon 2 plus C3 epsilon 3 is equal to 0. And we are saying that these all of them are not 0. We are assuming that all of them are not 0. Okay, so this is assumed and we are assuming this. That means C1 into 100 plus C2 into, or we can call it better in better manner like this, that not all of C1, C2, C3 are zeros. Okay, that means this plus C2 into 010 plus C3 into 001 is equal to 0, but that will imply C1 is equal to 0, C2 is equal to 0, C3 is equal to 0. That is all the three of them are zeros. So that is a contradiction there. That means we get that uh, They are linearly independent. Okay. Uh, Note these guys sitting here because they are important when we move on. Okay, and let's see example 13. Let F be a field, and in Fn, let S be the subset consisting of the vectors epsilon 1, epsilon 2, etc., epsilon n, and they are defined likewise like this 1, 0, 0, 0, 1, 0, 0, 0, etc., 0, 0, 0, etc., 1. Let x1, x2, etc., xn be scalars in F and put alpha is equal to the linear combination of x1 epsilon 1 plus x2 epsilon 2 plus etc. xn epsilon n. That means that is nothing but you can write it like this x. When you calculate it, you get this. You're going to get that is equal to epsilon x1, x2, etc. xn, the n tuple, you get like this. So alpha is equal to this. This shows that these vectors epsilon 1, epsilon 2, etc., epsilon n are spanning Fn. Each element from the Fn can be spanned like this. So since alpha is equal to 0 will obviously imply x1 is equal to 0, x2 is equal to 0, etc., xn is equal to 0. The vectors epsilon that will mean the vectors epsilon 1 etc epsilon n are linearly independent, right? So the set S is equal to the set of all epsilon 1 etc epsilon n is a basis because basis for Fn because it is a set which is linearly independent as well as it is spanning the whole of Fn, forming all the vectors by their linear combinations, right? So we are calling this particular basis as standard basis of Fn. Fn is nothing but Rn, the usual Rn we are talking about. So that is an important information from there. Example 4 says that suppose if P is an invertible matrix which is having the order n by n, with entries coming from the field F. Okay. And we are calling the columns of P as P1, P2, etc., Pn like this. This column will be P1, this will be P2, etc. This column will be Pn. The columns of Pn will form a basis for the space of column matrices Fn cross 1. Fn cross 1 means set of all column vectors where the entries are coming from n. They are n tuples arranged as a transposes. Okay. So if you are taking the column matrix X, okay, that means X is an n by 1 column matrix. Px, if we consider Px that is equal to P is here, the column vector is here. When we just do the multiplication, you get x1 is multiplied with P1, x2 multiplied with P2, etc. xn multiplied with Pn will form Px, right? So what you get is if Px is equal to 0, the you can just cross the multiplication of this matrices and you can see that this term is equal to what you obtain as a matrix which is an n by 1 matrix. Okay, since Px is equal to 0 has only the trivial solution. Why? Because this P is an invertible matrix, which is a trivial solution. X is equal to 0 since it is homogeneous. It follows that P1 etc. Pn is a linearly independent set. Definitely. So Px is equal to 0 means all of them, the coefficients are 0. So you get the property about the linearly independent set. Why does it span Fn cross 1? That is a question. Let For that, let Y be any column matrix. Okay. So if X is equal to P inverse of Y, suppose if it is P inverse multiplied by Y, then Y is equal to Px. Right. So that means Y is equal to x1, p1, etc. xn, pn. That means Y is written as a linear combination of these p1, p2, etc. pn. So that means it is spanning all the elements inside fn cross 1, capital Fn cross 1. So that means it acts as a basis because it is linearly independent and it is spanning. Example 15 gives us a notion about homogeneous systems and the basis and all. Let A be an m by n matrix and S be the solution space of the homogeneous system Ax is equal to 0. Then A if R is the row reduced echelon form of this A, okay, then we know that Ax is equal to 0 and Rx is equal to 0 will have the same set of solution. That's how we usually do when we are dealing with the system of equations, right? So if capital R has R non-zero rows, R is a row reduced echelon matrix. So we know that the first entries non-zero entry of each row will be 1 and the entries below and above that 1 will be reduced to 0 final in the final step. So suppose if R has capital R has small r non-zero rows, then the system of equations Rx is equal to 0 will express small r among the x1 etc xn unknowns in terms of the remaining n minus r unknowns xj. So suppose that the leading non-zero entries of the non-zero rows occur in the columns k1 etc kr. So that means see suppose if this is r and we are saying that the first non-zero entry which are coming in the rows will be 1. Suppose if the 1 is coming in this column, okay, in this column the 1 is coming here the first and here everything is 0, so let that be labeled as k1, okay. And then suppose if the second non-zero entry that is 1 is coming here, that is coming under the label k2, okay, and so on. So such columns are called k1 k2 etc kr, okay. And then we are doing j, then we are finding a j, defining a j that is equal to the set of all indices 1 to etc n minus set k1 etc kr, okay. Maybe you can call it L1, L2, etc. L of Ln minus R, simply to understand that there will be n minus R elements in J. Okay. Then the system Rx is equal to 0 has the form. How will it be? Okay. So here you have a 1 here and rest of them will be 0 in this row. So when we multiply, the first thing that comes is 1 into the k1th variable, okay, that means that is coming here 1 into xk1 plus then you have all the elements that are coming indices that are coming from j, okay. So you can call it as c1 l1 x l1 plus c1 x c1 L2 x L2 plus etc plus C1 n minus L n minus R x L n minus R is equal to 0. That will be the first set of equation. Okay, and that varies from this 1 to r. Okay, so what is happening here is a statement which is set here. That means the x the elements the elements which are the unknowns xk1 etc xkr, they are equated to, that is here you can see that xk1 is equal to negation of summation over the index j c1j xj. Similarly you have xk etc xkr is equal to minus summation over j crj xj. So here what you are getting after the computation is that the solution for xk1 etc xkr are found in terms of xj's where j's are coming from the capital J, the indexing set capital J. And also we know that capital EJ, if that is a solution obtained by setting xj is equal to 1 and rest of the xi's are 0, then we assert that the n minus r vectors ej, j in j form a basis for the solution space, because we know earlier from that earlier from the earlier example that they are linearly independent as well as they are spanning, so that will form a basis for the solution space, and the solution space has n minus r vectors. So all the ej's where j are varying in j, how many elements are in capital J? N minus R. Okay. So you can read through the rest of the paragraph to understand that the solution with this property is unique. And we are moving into the example 16, which says that the subfield f of complex numbers, we have an f, and capital V be the space of polynomial functions over f. These functions are written simply like f of x is equal to c naught plus c1x plus etc plus c n x raised to n, and we are saying that the set 1 x x square x cube etc. Instead of that, here we have fk of x is equal to x raised to k, where k is equal to 0 1 2 etc. So we are saying the set sitting here is a basis of v. Clearly it spans v, because every polynomial can be written as a linear combination of this, and also f is equal to a general f is equal to this. Okay, and definitely it is a linearly independent set, because you can see, suppose if we are taking the linear combination is equated to 0, you know that c naught plus c1x plus etc plus c n x raised to n is equal to 0. That will certainly imply c naught is equal to 0, c1 is equal to 0 etc cn is equal to 0. So that will imply that the set we are talking about here, which is the set 1 x x square x cube etc., is basis for the set of all space of all polynomial functions over f, and that is an infinite set. So that is for today's video lecture, and in the next video lectures we can see theorems and some propositions related to this basis and dimension. Please go through the section rigorously and try to solve the exercises related to it in the section. So thank you.